Okay, so up to the very end of our lesson on Thursday, we were drawing Lewis diagrams using what we called the valence rule, or essentially we were determining how many lines or bonds were coming from each of the various atoms depending on how many unpaired electrons they had. So if I was dealing with something like a chlorine, well, you tell me, how many lone pairs and how many bonds come from a normal chlorine? Yep? 3 lone pairs and 1 bond. And that comes from the fact that group 7 has 7 electrons in it, needs to pair 1 more up. We need to have 1 bond on that. And working our way across, oxygen, what's it going to have? What are we going to have there? What do you got, Cole? 2 lone pairs and 2 bonds, because oxygen normally has 6 electrons, and therefore it's going to form 2 bonds. And again, continuing, nitrogen, who's got it? Yep, Cameron. 1 lone pair, 3 bonds. It has 5 electrons in its valence shell, and therefore it needs to share with 3 others to get to 8. And carbon, what's it look like? Yep, it's going to have 4 bonds. And we call that the valence rule, because remember, valence means the power to bond, and that comes from the fact that it wants to pair up such that it has a full outer shell or has 8 electrons in that outer shell. We call that the octet rule. And then at the very end on Friday, I introduced you to something called a coordinate covalent bond, where some atoms like oxygen that need 2 more can shift their electrons around and just kind of stick onto a lone pair. And then that resulted in some compounds that weren't behaving the way they normally behave. We drew a bunch of chlorine compounds like chlorate and perchlorate, and the chlorines in those compounds definitely did not look like a normal chlorine. And so what we need to do is we need to come up with a plan now to draw Lewis structures that involve these atoms that don't look like they normally do, all right? And I call them ugly structures. They're ugly. They don't have the same connections that a regular one would have. So let me first define the difference between ugly and nice. So you can write down the top part. Don't bother writing down the valence rule. We know that. We don't need to write that one down. So write down the difference between a nice structure and an ugly structure. Now, these terminology that we've got here, a nice one, that it doesn't have any coordinate covalent bonds and everything looks the way it should. You're not going to find that in a textbook anywhere. That's just me trying to break this into chunks for you so that it can make some sense. So the ones that we did the last day that have all these nice little, here comes all my emails, get out of the way, that has all the proper number of bonds and lone pairs, I call them nice. Essentially, they do not contain any coordinate covalent bonds. That's what makes them nice. And then the structures that do contain a coordinate covalent bond, well, the question, I guess, is asked, how do you know where to make the bonds? How do you know which one gets more bonds than it should? How do you know which one gets less bonds than it should? And a series of rules have been determined or have been, written down that allows us to get these. So again, the valence rule, it's what we just talked about. It's what determines the number of bonds that they should normally have under normal conditions. Just to start us off nice and easy, let's do a couple of nice examples. All right, so we'll just draw those up. No need to panic on these. All we're doing is sticking them together, essentially a little bit of a review from the other day. So again, hopefully through enough repetition, you see carbon is going to have 4 bonds. Again, if you're not sure where to start, draw them all out so that we can stick them together in some way. 2 hydrogens. Again, you can't just stick things together. You stick those 2 hydrogens together. Okay, you've made a hydrogen molecule, but that's not the molecule we want to draw here. So again, start to connect them together. See if you can get everybody happy, get everything to fit. Does somebody have a structure for that first one that they can explain to me how to draw it? Yeah, what do you got there, Lily? Excellent. Yep. If you're making the connections, right, it's looking like that. We'll put one there, we'll put one there. And that is just a funny picture. That's just fun. That's, you know, I could make cartoons if I just started with Lewis structures. I could be a cartoonist. That's a frog. That's a teenage, no, it's a turtle. It's a Teenage Mutant Ninja Turtle. Looking to the left. Oh, that's just silly. Okay. No? Put a headband on him? No, I'm not going to do that. That would just be too far. Okay. Does somebody have the next one? Don't make me draw another picture like that. Does somebody have the Lewis structure for this already figured out? What are we doing? Yeah, Cole, what do you got? Both nitrogens have a lone pair. Excellent. It's a good structure. Again, these are nice because all of our atoms are behaving the way we would expect them to behave if they are simply bonding to fill that outer shell, starting with its atom as we see it on the periodic table. All right? So those are pretty straightforward. Of course, now, we already did that one, so we're not going to bother that. Of course, now we've got to figure out a way to draw these ones that they don't behave the way we want them to behave. Now, unfortunately, we need to learn a series of rules. In the first period class, I already put together some chart paper with those rules. I don't know if this is enough information for you to write down. I don't even know if you can make sense out of my chicken scratches here. I will bring them all up, and you can write them all out. There are 6 rules. And if you want to try to, shorten this up, you can. Rule number 1, add up the valence electrons for each of the atoms. And if it's an ion, you have to add an electron for each unit of negative charge and subtract an electron if it's positive. So what did I write down here? I just put total valence electrons, add an electron if negative, subtract electrons if positive. That's the essence of that rule. Just like when we started and we were doing Lewis diagrams of ionic compounds, I said to you one of the most important things is that the number of electrons you have at the end is equal to the number of electrons that you have at the beginning. And that's what we're doing in rule number 1. We're totaling up our electrons. And again, if you want to make that shorter, 1 we've already seen skeleton electron or skeleton structures. Those were the ones like the carbon structures that I showed you at the end of class the last day, where I screwed up that first one very badly, if you want to recall the mistakes I made. That's funny. So once you build, or once you've counted all the electrons, we want you to create a skeleton structure. The skeleton is only made up of single bonds, with the atom with the highest valence at the center. Now, this doesn't make a lot of sense right now until we actually get doing it, right? And that's why I put these rules kind of on a short form off to the side, so that when we start to do them, we can always make reference back to the rules. So we calculate them all, we count them all up, then we make a skeleton structure. The skeleton's made up of only single bonds. By the looks of it, everyone's writing down the rules all long form, which is fine. So in the next slide, when I bring it up, I'll just bring it up and let you just write, and then we'll talk about it at the end. Again, you can see there on my board, there's 6 rules. Oh, man. Leave some space. Well, that's what we're doing. Let me see what you got. Where are you at?
I have the last line. Central.
Right there. You're going to start right down there. Yeah. All right. Don't lose your focus. Ignore the dudes at the back that want to chatter constantly. Yes, you too. That's what I'm talking about. Okay, let me go over these rules again, now that you've written them. Again, in a little shorter, more digestible fashion, and then we'll do an example, and hopefully it'll become clear. Like I said earlier on, just like I said when you were drawing your Lewis diagrams for your ionic compounds, and we were just simply transferring an electron, I said to you in the end, a good check is to make sure that we've not lost or gained any electrons, because it's the electrons that hold chemicals together. And depending on how many electrons, and I'm talking valence electrons, how many outer electrons that a bunch of atoms have when they come together and bond, that determines exactly how they bond. So it's all about counting electrons. So that's the first step. So we start to build our structure by plucking all the electrons off. Sometimes I say, when we total them, imagine that you're literally taking all the valence electrons off and putting them in a bowl so that you can start to build your structure from scratch. The second thing was to make a skeleton structure and use all single bonds. So there you can imagine that you're taking those atoms, now that you've removed all the electrons, and you're sticking them together with single bonds, taking 2 electrons from your little gathering of electrons to make each of the single bonds. So now we're building the structure by using those electrons that we've counted. Once we've built our skeleton structure, we'll have all these extra electrons left for lone pairs. So we simply start to put the lone pairs around all of the atoms, starting with the outside atoms. The reason we do that has something to do with electronegativity, but you don't have to worry about it. You just start by placing extra electrons around the outsides. If you have any electrons left, you then move to the central atom and put any extra electrons onto the central atom. But sometimes you don't have that. Sometimes you've run out of electrons and there's nowhere, there's no other electrons left in the bowl from counting them, that you can't just start adding electrons, right? That's the move that's illegal. You can't just add dots just for the sake of finishing a picture. If there are atoms that don't have the octet rule satisfied, in other words, they're not happy, what we have to do is we have to shift electron pairs around that already exist to create double or triple bonds. And once we're done the structure and we've checked that we haven't added any extra electrons, and we've checked that they're all happy, octet rule, except hydrogen only needs 2, then we've got a good structure, okay? So let's do some example structures here. So we'll start with SO3. Now you might imagine some way of making a ring out of that particular thing with all these sulfurs looking like an oxygen and just having them like hold hands in a ring. But these are not the case. This is a sulfur trioxide molecule, and in all of the ones that I'm going to give you, there will always be a central atom, and then there'll be other atoms hanging off from that central atom. Step 1, count the valence electrons. How many outer electrons in sulfur? And we'll just take it. These are just things that you can just tell me. 6. It wants 8, but it's got 6. 6. And how many electrons in oxygen? 6, but there are 3 oxygens, so 6 times 3. There's no charge on this, so we didn't have to add or remove any electrons. So now we just have a total of electrons. How many electrons are we dealing with? 24? 24 electrons. So in theory, you can imagine I picked out some sulfur atoms and some oxygen atoms. I picked off all the electrons, put them in a bowl, and now I've got 24 electrons to glue everything together. Next, we make a skeleton structure. Sulfur in the middle and 3 oxygens connected. They will never be in a straight running chain, all right? They won't make a ring. These are all made up of a central atom with something bonded off of them. If you've got a whole bunch of a certain type of atom, they're the ones hanging on the end, because it's always a very symmetrical molecule. So here's the question. How many of those 24 electrons did I use to make those single bonds? Because essentially what I'm saying is, let's now start taking electrons from our pile and start gluing together our atoms with bonds. How many electrons did I use there to make that skeleton? Yep. I did not use 12. Nope. I used 6. Each bond is made up of how many electrons? 2. So I've used 2, 4, 6 electrons to make those 3 bonds. So since I've used 6, I must subtract those 6 electrons away, and I got to see how many electrons I have left to complete the structure. And by the looks of it, it's 18 electrons. Now I take those 18 electrons, and because my skeleton's done, I start filling the outside atoms until they're full, until they have 8 electrons in their outer shell. So now I start counting out my 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I've filled all the oxygens with 8. They're all happy. But you'll notice the sulfur, is it happy? No, it only has 6. Now, the wrong thing would be just to add 2 more dots. But we really don't have any more electrons to add. I started with 24 electrons, and in that structure right now, there are 24 electrons. So I can't add any more dots. So I need to now, number 5, shift lone pairs to satisfy the octet rule. There's all kinds of lone pairs here. It doesn't matter which pair I choose. I'm going to just choose this one. We'll take this lone pair here, and we'll shift it into a bond there. You could have picked a lone pair off of any of the other oxygen atoms. It would have still been correct. It would actually be the same structure. So now I'm going to rewrite the structure with now my new orientation in the pairs that we've changed. So here's the sulfur. It now has a double bond with this oxygen because it shifted a pair. Now there's only 2 lone pairs because one of the pairs became a double bond. And the other oxygens remain unchanged, and they have 8 electrons around them. Now the 2 things that you should check. If you want to make sure that you've got a proper structure, number 1, the check that you can do there is the electron total, the proper total. Do you have a proper total number of electrons? In this case, started with 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I have 24 electrons. And the other thing is everyone happy? Oops, that's terrible. Happy. Octet rule. Right? Is everyone happy? And is everybody happy in that structure? 8 electrons around everybody? Therefore, that is a good structure. This is not an ion. This is a neutral molecule. It's a sulfur trioxide molecule. And so I don't need the square brackets. That's done. That's a good structure. And nowhere at any point in time did we worry about if anything looked right. And that's the important thing. We simply build it. And if we follow our rules, then we will have a proper structure. Question, Braden? When? This picture here? No, because I'm out of electrons. You have to count the electrons. If you're just adding dots, then you're making a completely different molecule. If you added 2 electrons to that, you would then have SO3 with a -2 charge, and then that becomes a sulfite. And that's completely different than sulfur trioxide gas. And the only difference is 2 electrons. So no, you can't add 2 electrons because you don't have 2 electrons to add. Okay? If I changed the molecule to a completely different thing, I could, but that wouldn't be that then. It would be a different molecule. All right? We'll do examples where we will have enough electrons to go to the center, right? And then we'll talk about what happens there. Let's do another one. Again, this is the type of thing where if you've got a pencil nearby, start counting valence electrons, start building skeletons, take the electrons to build them. Difference here is I've got a -2, so we've got to add a couple of electrons to the pile. What do you get for a total number of electrons? Did you do it yet? No. Darn, there's a mistake in this. That's -1. It's -1. Yep. I changed it from this morning's, and I'm going to fix it. It's -1. Oops. I'll just put minus. That's gets it across. -1. Total electrons. Nitrogen, what do we got? How many for nitrogen? 5? 5 plus 6 times 2, negative charge plus 1. If I left that as -2, we end up with a very special type of a compound which does exist but is highly reactive. What happened when it was -2? What did you notice about the number of electrons? 19, which is what? Odd. And why do you think odd numbers of electrons are not a good thing for chemicals? Any ideas on why an odd number of electrons isn't a good thing? Yeah. It becomes very unstable. Why do you think? What are we going to end up with if we continue to draw the picture and have an odd number of electrons? This is automatically going to happen by the time you get to the end of the structure. What's going to be the case if you had an odd number? Yep. You're going to have an electron that's by itself. Not is it only going to be a lone pair, but it's going to be all alone. And chemicals that have lone electrons are very reactive. Why do you think they're very reactive? What are they going to do if they've got an electron that's all by itself? They might try to get rid of it. What else could they do? What's that? Desperately gain another one from somewhere else. So they're very reactive. We don't want to deal with those yet. We'll talk about those in grade 12. So what do I got here for a total? 12, 13, 18? 18 electrons. Skeleton structure, only 2 O's. Looking like that. How many did I use to make the skeleton? 4. -4, 14 left. So let's start filling from the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got 2 more left. I can't put them on the oxygens. Where are they going to go? Yep. On the nitrogen, 13, 14. You'll notice nitrogen isn't happy yet, but that's okay. But you can't add any extra because I'm out of electrons. So what am I going to do to take care of nitrogen? What are we going to do here? Yep, Lily? Yeah. Yeah, and it doesn't matter which pair. I'll just take that pair for no reason. It does not matter which pair. So now I rewrite. I now have a double bond on that one. Still the single bond on that one. Now this one is an ion. What do I have to do to complete it? Yep. Yeah, square brackets and the charge on the outside. All right? That's exactly like we did when we had the ions. Like, remember when we did the ions and we made a simple chloride ion and we put the things around it? That's the same thing. I have to put a square brackets and a charge around it. Same thing here. Question?
You always have to take the dots away from
One of the O's, the pair of the dots are actually becoming the double bond. So once you move it, now the pair of dots will be gone, and there'll now be a double bond in that little spot beside it. We can still check to see if we've got the right number of electrons. 18, right? So once you're done moving everything around, 2, 4, 6, 8, 10, 12, 14, 16. What the heck happened here? Oh, I didn't finish my structure. That's a good check. There I was in a hurry, right? I didn't put my lone pair. I counted. Uh-oh, that's incorrect. I needed that lone pair. Good catch. That's me worrying more about making this bond than anything else. So now we check again, make sure. 2, 4, 6, 8, 10, 12, 14, 16, 18. Excellent. Now we've got a proper structure. I lost those 2 electrons. It's a good check. All right? Let's keep going. We'll do some more. Without me writing it all down, what'd you get for a total? 20? 26? 26 electrons. We use 6 to build the skeleton. 20 left. Start distributing. Start from the outside. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Is everybody happy? Yep. Have I got the right number of electrons? 26? Yep. That's it. That structure's done. No need to do any moving in this case. All I need is the square brackets. All right? Just to kind of put this in perspective, we're teaching you how to draw ions, but if I asked you to draw, what is this? What is BrO3 again? A little bit of a review back. What is BrO3 as an ion? What's the name of that thing? Cool? It's a bromate. So if I asked you to draw sodium bromate, all right, NaBrO3, and I said, draw the Lewis structure for sodium bromate, you would draw a bromate, and then you'd need a sodium +1 ion to go with it. So Na, it gave all its electrons up, plus, that's the Lewis diagram for sodium bromate, because it's got a sodium ion and a bromate ion. Okay? So what we're getting you to do is draw the Lewis diagrams for some of these polyatomic ions. That is a chlorine, by the way, folks. That's not carbon iodine and then 2 fluorines. It's a chlorine and 2 fluorines. And this is an example of an ion with a +1 charge. And man, I hope I didn't screw that one up. But it looks good. We're checking for an even number of electrons when we get to the total number of electrons. We don't want any of those radicals. For those of you doing the math, and hopefully you're ahead of me, 7 plus, and then 7 times 2, and now to make a +1, right, we need to remove an electron, so I need -1. So again, this is new from the last one. That +1 charge means that we have to subtract an electron away. So what is that? 21 minus 1, 20? 20 electrons? 20 electrons. 1 chlorine, 2 fluorines. I'm thinking the chlorine is the guy in the center. We've used 4, 16 electrons left. Load from the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Did I count right? What's that? I missed the bonds. No, but I mean, did I count my extra electrons anyway? Let's count them all up just to make sure. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We started with 20. Is everybody happy? Yeah, that's a good structure. We just need to put the square brackets around it. +1. Or 1 plus, or just plus. Doesn't matter. So if you've got a positive charge, taking an electron away. Okay? All right. How many more have I got left? I think I got a couple left. This one, and then one other, and then practice problems. What we are doing right now is the bottom half of that little homework sheet that I gave you the other day. I gave that to the morning class today because I didn't get as far as I did with you guys, and most of them were able to complete it just during class time. So we'll make this due tomorrow, and when I get you a chance to work here, you'll be able to finish that off quite quickly. It's pretty straightforward. Some of you are to the point where you're moving electrons around. Move as many around as you have to make everything happy. Somebody have a structure for this, and I'll take it, see if we got the final structure, and then we'll work backwards and work our way through. Somebody want to give it a shot? It's a tricky one. This one's trickier than the last ones. Cole, what do you got? And each have a lone pair. What's that? Square brackets +1. That's a good structure. That's what it is. Nice job. Again, the oxygen looks goofy. It's behaving like a nitrogen, but that's okay. It's behaving as it should, and it's got the full outer shell. We've got the right number of electrons. What was that total number of electrons? 10 electrons? 10, making the skeleton, nitrogen with an oxygen, -2, 8 electrons left. It doesn't really matter which one you start putting the electrons on, but whatever you start, you should fill it right full. Don't try to distribute them evenly or something silly like that, because it never works out well. 1, 2, 3, 4, 5, 6, 7, 8. You could have started with the nitrogen. It wouldn't have made any difference. Oxygen is good. Nitrogen is short. Goodness, we've only got 2, 4, so it's short 4 more electrons. It needs access to 4 more electrons. Take a pair here, make a bond. Take a pair there, make a bond. And that gets you the triple bond with the lone pair on it. All right, that's kind of a neat one. So there is an O. And one last one, and this actually is a nice structure. We have already drawn this structure, but what I want to illustrate to you here is that you can use these rules to draw whatever structure. Any of the nice structures that we've done will still be able to be drawn with this. You could draw this by just drawing it. It's a nice structure, but go through it just like we've done. Go through it, adding electrons, checking for happy guys, moving electrons around, and you'll see that we get the same structure that we would get if we just drew it as a nice structure. Ah, that's funny. Can you hear it? There was again, it was the little cow stuck in somebody's backpack. Oh. did you add all the electrons up? But it's not happy yet. You gotta move some electrons around. That carbon is just gonna be grumpy, sorry. How many electrons? 4 plus 12, 16 electrons. Make sure you're writing these down. I'm just kind of jumping ahead, right? 16 electrons. Carbon, oxygen, oxygen, what did I use? I used 4. 12 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Carbon's not happy. What am I doing? What am I doing, Rachel? So take one there, right? Put it there. Do it on the other side as well. Perfect. Take one, put that there. C with double bonds, now with only 4 electrons. And we did that example when we were talking about just straight double bonds, right? That's carbon dioxide. Oxygen looks the way it's supposed to look. 2 pairs and 2 bonds. 2 pairs and 2 bonds. Carbon has 4 bonds. So you can also draw nice ones with this method. You're just calculating up the electrons. So there are some practice problems to work on. I've given you that sheet, which we will make due tomorrow, and trust me, you'll all rush to finish the sheet before you do the homework. I know the way your brains work. So when you're done, just hand that in, all right?